from where we left off last time on geometry. We were talking about all these crazy angles and these things and secants and chords and circles, and sometimes the lines would cross inside and sometimes they'd cross outside. And now, today, we will focus on lengths more so instead of angle measurements. So, same type of thing is going to apply here. Either our secants or our chords are going to cross inside our circles, or they will cross outside of the circles. And if they cross on the inside, it's not necessarily at the center of the circle. More than likely, it's not going to be on the center of the circle. So if you see here these two secants, or if you want to just chop off the line parts here, we could say, well, these are chords. And where do they cross? Well, they cross on the inside. So here's the kind of formula we're going to use here. And this kind of uses, this is all based on kind of similar triangles. If you imagine drawing in a couple lines here, we could show that these two triangles are similar and therefore their sides are proportional. So really this is all based on, what I have here is based on two ratios being set equal to each other and cross multiplying. So that's what's really happening. We're not going to look at a proof of it. It's not as easy as you might think. But this is what we're going to consider here. Okay, when I talk about the inside part times the inside part, I'm focusing on one secant or one chord. And one of the inside parts, well, that's A. The other inside part of the same secant or chord is B. So if I take the A times B value, whatever they may be, then I can set that equal to the other inside times inside part, which again, I go to my other secant or chord. And those two pieces are my C and D. So I set this up, and out of these four variables, A, B, C, and D, typically three of them are going to be numbers in the end, and you're just going to use some algebra and solve for the one that's missing. Now, these secants, or chords, if you would, we can just kind of chop off these parts here. But still, these are still secants. They're not entirely chords, because chords are only on the inside of the circles. But they cross on the outside. So what does that formula particularly look like? And this also uses proportional sides from similar triangles. But we're not going to get into the whole proof again. Now, when I talk about outside times the whole thing, so if I'm talking about this thing right here, the whole piece is all of this. And how would I represent all of this collectively? Well, that would be the quantity, whatever x plus w is. And the outside part, well, that's just the piece on the outside, which in this case is x. So if I take x times the quantity, x plus w, the whole thing, then I can set that equal to the other secant slash chord. So the outside part for it is just the y piece. And the whole thing together would be the y plus the z. So that's the formula we're going to use if they cross on the outside. It'll be outside times whole equals outside times whole. Now we do have a special case here where maybe they do cross on the outside, but one of our pieces is instead a tangent instead of a secant. Well, we're still going to use technically the same formula. The outside times whole equals outside times whole. So this piece might, be this P right here. The whole piece would be P plus Q. Okay, there's P, there's Q, so that's the whole thing. Now, you could repeat outside times whole with the tangent part, but just know that the outside piece and the whole thing are really the same thing. Okay, again, let me repeat that. This is the outside piece, but it's also the whole thing because there's nothing inside. So we can call this just the tangent piece squared. So we could just say that's equal to whatever that piece is hanging out here, that tangent piece, square it. So let's look at a very basic example to begin with. Okay, so we see these two lines cross on the outside. So we're going to be using outside times whole equals outside times whole. And again, I will personally write this out when I'm doing the problem even, okay? So let me identify one piece here, and that would be this guy. So the outside piece would be this part, the y. The whole piece would be the y with the 6. So I'm going to write this in parentheses because it's two pieces there, y plus 6. And then I want to go to my other piece here. Now, its outside part is the 7, And what's the whole length? It'd be the 7 plus the 9. Now you can write in parentheses 7 plus 9, but that's going to be kind of silly because 7 plus 9 is just 16 overall. So if you know what the answer is, just go ahead and say 16. So now I need to solve this. But how am I going to solve it now? Well, first, over here on the left side, I'm going to need to distribute this y. So y times y is y squared, and y times 6 is 6y. And then over here, 7 times 16, that is 112. So if I look at this, this kind of looks familiar, like a problem that maybe we've been working on in terms of some portfolio questions. We have a squared term, a not squared term, and a constant. This is going to be a factoring type problem. So what you're going to want to do is move everything over to one side. So we're going to want to subtract our 112 over. So I have y squared plus 6y minus 112 equals 0. Now we can try to factor this. I don't know how much luck we're going to have here, but we could do y times y, and this is more the easier factoring problem. We need two numbers that multiply to be negative 112, but add to be 6. So let me move some of this out of the way here. So let's see. 1 times, oh, where'd my pen go? Pen, where'd you go? There we go. 1 and 112. But the difference between those two things is only 111. So, here's my difference, and here's the two things that will multiply to equal 112, really negative 112. So this could be negative 1 and 112, or negative 112 and positive 1, but the difference is going to be either positive or negative 111, which is definitely not 6. 2 times, 56? So I could say that's negative, and the difference would be 54. 3 can't go into it. Can 4 go into 112? That's where I need my calculator help here. Yeah, 4 can. We could say negative 4 times 28, but still the difference between that's 24. 5's not going to go into it. Will 6? No. Will 7? Yes. 7 times 16, which we already knew that from over here. What's the difference between those two? 9. So we're getting closer. What about 112 divided by 8? Yeah, 8 works. 8 and 14. Oh, and look at the difference between there. There's our 6. So here's our two numbers, negative 8 and 14. So we set each one of these equal to 0, and here we'll get y equals 8, and here we'll get y equals negative 14. Now, algebraically, yes, these are two good answers, but geometrically, we were looking for a length. So this negative 14, it's a good algebra answer, but not a good geometry answer. So that is an extraneous answer. So our only good answer is y equals 8. All right, example 2. Look at this mess. Holy cow. What on earth are we even going to do? There's so many numbers in here. I don't know what to do. I'm confused. I'm just going to give up, right? That's the thing to do. We'll just give up. Or better yet, let's just make up numbers, right? Yeah, I mean, look, that's 9, that's 9. Hey, x looks pretty close to that. Maybe it's 10. I don't know. We'll say that. Maybe y's 10. Sure. Why not? Let's do that. I don't think so, friend. Let's solve this thing. All right. Few things I want to notice here. I see a point of intersection here. I see two lines crossing here. I see two lines crossing there. There are up to 3 of these inside problems here. We just need to take our time and break them down one by one and see which one we can do now or which one we may have to wait and do later once we figure out other values. Okay? So let's start with, I don't know, let's start with this guy, because when I look at these two lines, there are a lot of things, like every little piece has something there, right? Like this piece is 10, this piece is y, this is 9, this is 9, this is x. I'm already seeing I've got an x and a y going on here. So I'm not going to be able to solve this now, but you know what? It doesn't hurt to set it up because I'm probably going to have to solve it later, okay? So if we set this thing up, here's one chord, and we're going to have to do the inside times inside equals inside times inside. Okay, so I knock out the side, I just call it in. So I got 10 times y for one chord, and then this guy, where do I want to cut it off? Do I want to say this is an inside piece and that's an inside piece? Or do I want to say that this is a piece and that's a piece? How do I do this? Well, here's where they're specifically crossing, right? So I have to call this one inside piece and this the other inside piece. So one inside piece is this 9. The other inside piece is made up of two pieces, so I have to use parentheses, and it's x plus 9 or 9 plus x. So I'm going to leave that right there. Okay, I can't solve this. I have an x and a y, but I'm certainly going to leave it there because I'm probably going to have to come back to it later. All right, so we'll save it. Of course, it's attached. All right, so I'm going to erase all this so we can figure out somewhere else to go. So we talked about this guy right here. Okay, well that's made up of this piece, and it's made up of that piece. Well, if I notice, there's only an x here, which is cool, only one variable, but then this guy right here, we don't know the value of it. So again, we're kind of at a standstill. We don't really know where to go at this point. Let me do one little thing here real quick, because I think I might have accidentally deleted something. I did, because I accidentally deleted the center there. Ooh, that would have made the problem much more difficult. Okay, so anyway, that's the guy we saved. Let's go back and re-look at this here. We had that guy and that guy. And again, we didn't know the value of this piece, right? I mean, this is part of the radius, and this is another part of the radius, but they're not the same necessarily. So again, we're kind of stuck. We can't even really write anything because we're missing the length of that piece right there. So again, we'll maybe have to save it and come back to it later. Now here's the third place where we had some crisscrossing going on. So we've got that piece, and we've got all the way. We got to go all the way. You can't just stop at a certain point. Like you can't just stop right here and call that. That's not a full chord from here to here. You got to go all the way across. So if I look at this, all right, well I got two inside pieces connected up there. Cool. And then I got the 5 right here. And then I've got this piece. Well, I know part of it's 9, and then I don't know what this other piece is, and it's not labeled with anything. So what I might do is let's just make up a new variable. Let's call this piece z, if you will. Okay? So then this whole piece would be z plus 9. So we can definitely solve something here. So the inside times inside piece with this 9 and 15 should equal the other inside times inside. So I'm calling this piece 5. And this other piece here, that was our z plus 9. Okay, so we can actually figure out the length of this now, which related back to that last part we said we couldn't do because we didn't know what it was. Well, here we're actually going to figure out what it is. So we've got 9 times 15. So this guy's 135. And then I just need to distribute over here. Or better yet, I could just divide by the 5. Wow. Let's do something different here. Let's divide both sides by 5. So that 5 will cancel that 15 and leave me 3 left over. So now I just have 9 times 3 is 27 equals z plus 9. Subtract the 9 over, and z is 18. Okay, so let's clear some stuff out here. I don't want to erase my center because it's going to go away if I put my eraser there. Okay, so we know this whole guy right here, it's got a value of 18. Okay, perfect. Now, how does that really going to help me? Well, remember we said if we went back to, what was it, this guy right here? Now we can figure out what x is. So we don't need this anymore. So with this guy, let's see, here is one inside piece, x, times the other inside piece connected to it. Well, that would be 9 plus 9, which is 18, equals this inside piece, which is 9, times the other inside piece, which goes all the way over to there. So that's the 18 plus the 5, and 18 plus 5 is 23. Okay, so we got 18x equals 9 times 23. Let's see. That's 207. So now divide by 18, and x is, I don't think this is really going to give me anything pretty here. Well, it gives me 11 and a half exactly. So they're somewhere. So we've got x now. Now we just need to go back and get y. Well, remember this equation up here we wrote at the very beginning of the problem? We can now use that. So we've got 10y equals 9 times, well, 11 and a half plus 9. Well, that would make 20 and a half. So now 9 times 20 and a half, so I have 10y equals 184.5. Divide by 10, and y is going to give me, write it down here, that's just going to move my decimal point over 1 to the left, 18.45 exactly. And there I finally have x and y. Now, I had to use that inside times inside formula 3 times to finally get my x and y here. Okay, so you might run across some problems, and I made this problem up completely. Okay, you will not find this in any book or any practice worksheet or anything. I made this one up. I wanted this to try to be as tricky as I possibly could. And I think if I gave this to many of you on a test, you would struggle with it because you wouldn't really know where to start. So again, you need to identify how many potential problems there are in a problem here like this. And again, I noticed there were 3 locations where guys were crisscrossing. So I might have to use up to 3 formulas to solve this problem. And I did. I had to use all 3. And the last example we're going to look at here. Now, I pulled this out of the book, if you didn't notice. I didn't perfectly make this problem. Maybe I did. I'll take credit for it. This natural arch in Archies, I don't really know, National Park in Utah is an arc of a circle. Calculate the diameter of the circle. Okay, so we don't see the whole circle here. So let's imagine, let's get a circle if we will. We need a circle, and let's tone down the transparency here so we can kind of see what's going on. So I need a circle that's a little bit bigger than that, right? Because I need it to fit that arc. Let's stretch this thing out a little more. Does it fit that arc? Almost. It's getting there. How about now? Does that fit? Oh yeah, we're looking good. We're looking good. Okay. So you notice here, this is what we've got. We've got all the way from here, we got this chord, then this arc. We know this guy's 30. So now we got something to work with here. We want to know what's the diameter of this circle. Okay. Well, let's see what we got going on here. Let's make this a shade more transparent. There we go. All right, notice this says this piece is congruent to this piece on this chord. And let me make that chord just a hair darker. Let's go black, why not? All right, and this piece is perpendicular. Now, this is something we talked about back in the second section, that if we've got a chord in a circle that's being bisected and is perpendicular, then that means that this little piece here, this 30, if I were to keep extending it, what must be true about this particular segment I'm drawing in? It must go through the center of the circle. And if this piece is going to go from one side of the circle all the way over to the other, down below here, and it's going to go through the center, guess what that means is true about this line? It is the diameter altogether. Now here's the thing. I got to figure out what the rest of this is. I know part of the diameter is 30 feet. I don't know the rest of it. So I'm going to call the rest of it x. Okay? So x plus 30 is going to give me the full diameter. Now the 170 is the length of the whole chord. And again, I said it's being bisected. So we cut it in half, and it's 85 and 85. And now if you notice here, we've got an inside problem. These two chords are really crossing on the inside. So inside times inside equals inside times inside. I'm going to take the 85 and 85 from here and here. And then the other inside times inside will be my 30 times the rest of the diameter, x. Okay, so 85 squared, ooh, big number. 85 times 85 is 7225 equals 30x. Divide my 30 over, and I get something not exact. 240.83 repeating. Now, again, is this the full diameter? Not quite. It's almost the full diameter. We need to add in the extra 30 feet that it is lacking. So really, the full diameter is 270.83 repeating, where we at, feet. So now we could actually do some stuff with that. We could calculate the length of that arc. We could calculate, the area of that segment that we have trapped right in here between the chord and the arc. We could do a lot of things with it. So that is all for that video, and we will see you for the last video on section 12.5 soon. Adios.